Morning, guys. So today I'm going to make a video here for the Riverboat simulation that we did last week. So I'll put a key up for that. So the first thing that you had to do was just look for, will a change in river speed change the time required for a boat to cross the river? So as you did that, basically the way that you would play around with that, if I just keep the boat speed the same, I'll just keep it at 10. I'm going to move the river in. So if I've got the boat speed set at 10, and then the only thing I'm going to change is the river speed. So I can look here, took 10 seconds to go across. Reset it, change the river speed to 2. 10 seconds to go across. And so I can change this to 5. 10 seconds to go across. So point of that being is, with that question, is the answer to that is no. And you could put then the data I would expect here would be from the stuff like I just did, where you said the river speed was this, it still took 10 seconds. River speed was 4 meters per second, it still took 10 seconds to go across. So the river speed doesn't change the time to cross the river. And then for a constant river width, due east heading, what affects the time required to cross the river? So there, the only thing that does that is the boat speed. And so when you're going due east, that's constant, so you're not going up at an angle or down at an angle. And so you would just go in and change the boat speed. You'd see that the faster the boat went, the less time it took to get across the river, and put some evidence in there for what you did. And then the last one here at the beginning said what heading will minimize the time for the boat to cross, and so what direction. So I've got a maximum speed of 10, and so then you went in here, so 10 is my maximum speed. I'll leave the river at width and river speed alone, so I can hit play. It takes 10 seconds. Reset it. Now what happens if let's say I want to change this to 45 degrees. Hit play. Okay, that didn't make it faster, right? That took 14 seconds down here at the bottom. So let's change this. What about if I go up at, let's say, 20 degrees? How long does this take? 11 seconds. So that was slower than all of these at the original heading of straight across. So if I go up at an angle, down at an angle, all of those still take longer than if I just head straight across. So your answer then, as you're doing this, what heading will minimize the time? And that's due east. So, and you can put the data there, and I'm sure you did, about doing that. So if the boat's heading across the river, the time to go across really only depends on which part of its motion, and that's its speed to the east. So that was a key thing that you would figure out as you kind of played around and got some data at the beginning of this. And then this, getting this data table done kind of confirms that. So, you were given these two columns, and then you just had to run the simulation to get these. And what's important that you're able to do is that you see the river current here doesn't affect the time to go across. It does affect the distance downstream. And so those were the key parts of this that led into the second part of what you were doing. So the time required for the boat to reach the opposite bank of a 100-meter wide river depends on, so it seems like we're saying this over and over again, the boat speed. And explanation is that the other things don't affect it. Its due east speed is what determines how long it takes to get across. And now if we want to calculate the distance downstream, so the distance downstream is going to depend on, why is it doing, oh, this is weird. Distance downstream is going to depend on, it's going to depend on the river current and the time to cross. So we see those two things. So you could think about if it's going to move downstream, well, the current is going to be what moves it down, and how long it's doing that is going to dictate what's happening. And so we saw that up here in this table is that the time and the river current, and so some of you even noticed that river current times time equaled the distance downstream. So, so here when we have the waterfall, so how long is it going to take to reach the falls? Well, if the falls are 45 meters downstream and the current is 3 meters per second, so here it's going to take then for me to go that 45 meters, the time is going to equal the distance divided by the velocity way back from unit 1. And so that's 45 divided by 3, which is going to equal 15 seconds. So now I know 15 seconds till you go over the waterfall. What minimum boat speed is required to cross the 100-meter wide river before falling over? So you've got to go 100 meters in 15 seconds. So here, then what I've got to do is then I say my velocity is going to equal, velocity is going to equal distance divided by time, which is going to be 100 meters. Let's do 100 divided by 15. And so 100 divided by 15, let's see, 2 is 30, so 6 is 90. So it's going to be 6.67 meters per second. And then here, repeat this calculation, same thing. So, you know, you would just do the exact same process right there. So it's going to take you, looks like 9 seconds to reach the waterfall. So 100 divided by 9 at 11.11 repeating, or so 11.11 meters per second. Man. And then, so here we get to this next part, which is a little more conceptual. So we've got a boat beginning at A, heads straight across with a speed of 8 meters per second. The river water flows south at 3 meters per second. And so the boat heads towards B, but really ends up at C because of the river current. So we want to think about which would cause the boat to reach the opposite shore in more time. So if we bold the ones that do that, so it's a 100-meter wide river here. If I make the river 80 meters, so it's shorter across, it's going to take less time. But if it's 120 meters, that'll take more time. If the boat heads across the river at 6, previously in the problem it said it was at 8, so 6 is going to be a slower speed, so that'll take more time if it does that. The river flows at 2 meters per second or 4 meters per second. So earlier, one of the big ideas was that the river current didn't affect the time to go across. So it would just be those two things right there. And then say which of the following cause it to reach the opposite shore at a location south of C. So it's going to end up below there. So if it heads across the river at 6 meters per second, it's going to take longer, and then therefore it's going to get carried downstream more. If it heads across at 10, it's going to get there faster, so it wouldn't go down its stream as far. It would end up somewhere between B and C. River flows at 2 meters per second, compared to earlier it was at 3. So when the river was 3, it ended up here. So if the river is slower, it's not going to go downstream as far. But if the river's faster, it'll go downstream further. So those two right there. And then here we've got to figure out the resultant velocity. So this is what we talked about with the Pythagorean theorem. So anytime I have two quantities that are at a right angle or perpendicular to each other, I use the Pythagorean theorem for these. So in this case, I got the boat velocity, the river velocity, and so to get the actual velocity of the boat, that's going to be the square root. Control. So square root of That's going to be 15 squared plus 4 squared. So we'll go in, let's see, let me pause it while I calculate that. So that gives us 15.5 meters per second. What I noticed on some kids' work is that they were putting this in as 15.5 square meters per second squared or stuff like that. So, you know, if you think through the math, we're going to end up with the velocity is always going to be in meters per second. So I'm going to put this one in the key. I'm not going to solve it right now for us because we just do the exact same thing. So square root of 20 squared plus 5 squared. And so we'll put that in a minute. But then I wanted to look at this one because these last two were the same. So what you're going to do is here we have to find out the displacement, which is the vector version of distance. So the time to cross the river, just like we talked about earlier, is the distance across or displacement across divided by the velocity. So 190 divided by 15. So this is going to equal, let's see, 10 and 40, so 12.67 seconds. And then the displacement downstream, river velocity times the time. So we had figured that out earlier in this simulation. So river velocity is 4 meters per second times 12 and 2/3. So let's see, that's going to be 48 and let's see, stumped, 48 and 8/3. So 8/3, 48, 50.33 meters per second. So I think I did that right. And then what we would do for the displacement. So now we know that we have gone 190 meters across. We went 50.33 meters downstream. So that forms our right triangle, or our two quantities that are perpendicular. So I'm going to use Pythagorean theorem. So I'll do the square root of 190. Oops, wrong thing. Squared plus 50.33 squared and so then I plug those into my calculator. And so what I'll do now is I'll put in these final answers for up here at 11 and for 12, and so we'll have those in the answer key. And then here the last question says, so it's often said that the perpendicular components of motion are independent of each other. Explain the meaning of this statement and apply it to the motion of a riverboat in the presence of a current. So the meaning of that is that the horizontal part of motion doesn't affect the vertical part. And so here you see that the riverboat, its motion across the river only depended on its horizontal component. The river velocity didn't affect that. So the current didn't affect the time to cross the river. And what my hope is you were able to do is relate this to the horizontal projectile lab, so that with that we saw that the time to fall was completely independent of how far it went. And that's because the horizontal and vertical components are completely separate. So if after watching this you have questions, let me know, but hopefully this was helpful to you.